Alright, this is the second video in the series that I'm making about analog circuitry, which can do mathematical calculations. So today I am making the video about multiplication by constant, averaging different voltages, adding different voltages, and subtracting voltages. So first, let's look at multiplication by a constant, because this is the basis of all the other circuits. There are multiple ways to do this. Essentially, the effect that we want to achieve is given some input voltage, we want to multiply it by a constant, let's say 2, and have the output be 2 times the input. So first, let's look at the inverting config. So we use an op-amp, and the signal comes in through this path to the negative, to the inverted input through resistor R1, and then there's another resistor connected across, which forms the negative feedback from the output back to the negative inverted input. And the positive input is just grounded. And the output is just taken across the output to the op-amp's output to ground. So in this configuration, the gain of the circuit is this resistor R3 divided by this resistor R1. So in this case, it's 5K over 10K over 5K, which is 2. However, because it's in the inverting config, it's actually minus 2. So here, let's simulate our circuit and see the output. So we got the input, which is a sinusoidal wave with a period of 1 and an amplitude of 1. And the output is an inverted sine wave with the same period, but the amplitude is multiplied by 2. So it's as we expected. And you can derive this behavior mathematically by basically using the two rules of an op-amp, which is that the currents through both of these terminals are 0 because it has infinite impedance, and that with a negative feedback, the op-amp tries to equalize. It changes its output voltage such that the two inputs equalize in voltage. In this case, because the positive is grounded, this negative terminal is also grounded. It's 0 volts here. And the voltage drop across here is equal to then the current flowing into this point is equal to the current flowing out of this point here, because no current flows through here. And so therefore V2, the V in minus 0 volts divided by 5K, which is now V in over 5K, is equal to 0 minus the output over 10K. And if you simplify the mathematics, you get that equation of the gain being negative 10 over 5. One thing to note is that with this inverting config, you do have to supply a negative supply rail because the output is the negative of the input. If you don't supply a negative supply rail and just have it grounded, and then you have a positive input voltage, for example 2 volts, the output would just be 0 because that's the lowest it could go. The other thing is that we want to look at the input and output impedances of this amplifier circuit, this inverting amplifier. And the input impedance is, even though the input impedance of the op-amp's terminals are basically infinity, in this config, because we have a resistor here, the input is actually this resistor value. An input impedance can be determined by checking how much the current changes, how much the current drawn into the circuit changes when we change the voltage of the supply. And in this case, if we increase the voltage, the current does change. So therefore, the input impedance is not infinity, it's actually 5 volts. In fact, the current changes by the input minus 0 volts, because this is 0, divided by R1. So it's entirely determined by this resistor here. So in the case that we want to supply a very high output impedance signal, so for example from a very low voltage sensor, a very low current sensor, this inverting config is going to become problematic. So we have to make this resistor really, really large, and therefore this resistor has to also be large. in order to overcome the output impedance of the input signal. So let's move on to the next configuration, the non-inverting configuration. And in this case, what happens is that instead of the input coming in through the non-inverting, through the inverting input of the op-amp, it's straight away connected to the non-inverting terminal of the op-amp, which gives it infinite impedance. So this solves one of the problems that we had before. This gives the circuit basically infinite input impedance, and therefore it can drive very sensitive signals, very low current signals, I should say. And then the non-inverting input to the op-amp through the resistor is just grounded at this end. However, because of the way that this is set up, the gain can no longer drop below 1, because now the current across here is no longer 0 minus the output. It's 0 minus the actual input. So this introduces a 1 in the gain equation. And you can derive that by basically taking Kirchhoff's current law around this point. And the gain, mathematically, what it comes out to be is 1 plus this 10K, this R5, divided by R4. So in this case, it's 1 plus 10K divided by 10K. So that's 1 plus 1 equals 2. So in this case, the gain is 2, and it's not inverted. So let's have a look at that. As you can see here, the input is just doubled, and it's not inverted in phase, it's in phase. All right, so the last thing I want to talk about is what if we wanted to add a current buffer to a circuit, but we don't want to change the voltage at all. So in this case, let's say we wanted to use an inverting op-amp with a really high output impedance sensitive low current signal. In this case, we would add some sort of a buffer circuit before that, which has infinite input impedance and 0 output impedance. And an example of this circuit is the unity gain buffer, which is just the non-inverting config, except we make the gain 1. And to make the gain 1, we make this resistor infinitely large and make this resistor infinitely small. So this becomes a short circuit. Therefore, there's no, this becomes an open circuit. There's no connection here. And this becomes a short circuit, which is like this. So in this example, the output is exactly the same as the input, as you can see here. Exactly the same as the input. And the input and output impedances are infinity and 0. So we can put this as a buffer stage on other circuits. Next, I want to talk about averages. So how do we take 3 voltage inputs and output the average of them? And this is actually a very simple circuit. You basically just connect all of them to the same resistor value, and the intersecting node on the other side of the resistor is going to be the average value. So let me demonstrate that. In this case, so I have 5 volt, a sine wave, and a 2 volt as the input. And then the output on this side is all of them added together divided by 3, as you can see here. So this is the average output. Why does this work? Well, I'm not going to prove it mathematically. You can do that very simply by taking Kirchhoff's current law around this point. But essentially, a higher voltage is going to push current, and a lower voltage is going to sink current through this point. And the resistor values are essentially weights, so it's a weighted average. And if you make the resistor values the same, the weights are going to be 1 for every input. A disadvantage of the circuit is that the lower currents here, the lower voltages, lower voltage inputs will actually have to sink current. So you'll have to have a voltage source that can both sink and drive and supply or source current. And sometimes that's not the case for certain current sources. If you had a diode, for example, or like a PN junction of any kind, on the output of this voltage supply, sometimes you can't actually single source current, and in that case you have to use an addition circuit, a weighted addition circuit, which I'll go over later, in order to create the average. And then on this stage, we basically did what we said before. We added a unity gain buffer to this output circuit. The reason why we do this is because this average circuit has a input impedance that's not infinity. It's actually this resistor, right? Because it draws current, the input impedance is not infinity. So in order to make the input impedance really high, these three resistors have to be really high value. And because of that, it's not going to be able to drive a large load on the output anymore. So we have to add a current buffer to be able to drive a bigger load. So yeah, that's what the circuit is. Next, let's look at addition. So what if we wanted to add three voltages together? So there's two ways, right? One is we could use the average and we could just multiply by the constant, the constant being 1, 2, 3. So in this case, there are three inputs, so we could use this average circuit and just multiply by a constant of 3. So that's one way to do it. The other way to do it is through the addition circuit, where instead of taking the average here, we ground the output terminal of this sort of averaging circuit. As you can see, because we add this op-amp here, the op-amp will make both terminals the same voltage, and this terminal is 0 volts here, so therefore this is grounded at 0 volts. And then what actually happens now is now you have a Kirchhoff's current law around this point where the voltage drops across all three of these inputs has to add up to the same voltage drop across here, because the current has to be conserved around this point. So current entering equals the current exiting. And because of that, you have a summing effect on the voltages. And at this point, the voltage is actually the negative of the sum of all three of these voltages. So I'll just demonstrate that. All right, so these are the three inputs, and this is the output. It's the negative of the sum of the three voltages. So, for example, 2 plus 5 plus 0 here will give you negative 7. And then this is 1 plus 2 plus 5, which is negative 8, and vice versa, and so on and so forth. So, obviously, because we get a negative of that voltage, once again, we do have to supply a negative VCC to the rail here. I put another stage here to invert it again. So in this case, this is the inverting config, right? With the gain calculated to be 1. So 10k over 10k is 1. So therefore, this circuit stage is minus 1 gain. And so if you measure this total output across here, you can see that it is now the positive summation of these three inputs. Great, so that's the addition circuit. Once again, though, you can see that with the addition circuit, we also have a not infinite input impedance, because there has to be a current that flows through these resistors in order to make the circuit work. So ideally, you would have either these three resistors really large, or you would have a buffer stage before that. So next, I want to look at some of the subtraction circuits. So how do I subtract one voltage from another? So one way that we could do this, let's say we had a lot of voltages which are like A plus B minus C minus D plus E, etc. We could just use the addition circuit, except the negative voltages that we're supposed to subtract, we invert those voltages first. So in this case, let's say I wanted to have 1 plus 2 minus 3. The third voltage, we put it through this inverter that we saw before to become minus V3 out here. So in this case, let me demonstrate. So the input to V3 is 2 volts, and then the output is minus 2 volts in this blue line at the bottom. And then now we can basically use the same summing circuit to go, this voltage plus the negative of this voltage, which is to minus it. And I'll demonstrate that. So we want to have this voltage plus this voltage minus this voltage, right? So the output is here. So this is 5 plus 0 minus 2, and that gives you 3, as you can see. So yeah, this is a subtraction circuit. The other way to do this is to use a differential amplifier configuration. And this is a bit strange. When I first looked at it, it's like, why in this setup, why is this V1 minus V2? And actually, this circuit is pretty straightforward. Essentially, what this is an inverting amplifier, right? Except we don't ground this positive terminal. We make this positive terminal a half of the voltage that we want to minus it from. So there's a voltage divider here, which splits the voltage to be a half in this terminal. And then if you run the mathematics of the inverting config, it becomes half of this voltage minus this voltage is equal to the output voltage minus a half of this voltage, and because they're divided by the same resistors. So therefore, the two half voltages in that equation adds up to 1, and then it becomes this voltage, it becomes that voltage minus this voltage is equal to the output. So I'll just demonstrate that. So here we have 5 volts, and here we have a sine wave, and then the output is, as you can see, this green line minus this blue line, which becomes this red line, right? Let's check that. So here we got 5 minus 1, which gives you 4 in the red line, and so on and so forth. So this differential amplifier, again, just like the addition circuit, has not an infinite impedance because there's current flowing through both of these terminals. So we have to add buffers to these in order to drive sensitive voltage sources. Lastly, I want to talk about a circuit that exactly does that basically buffers the inputs. And this is the instrumentation amplifier. It's called an instrumentation amplifier because what happens is, within sensitive instruments, let's say a temperature sensor or a passive motion sensor or something like that, the voltages generated cannot drive a really large current because the energy input into the sensor is very small, right? For example, let's say a radio wave hits an antenna. It's not going to be able to drive a large current. So therefore, those sensors would have a really large output impedance. It's essentially basically like adding a resistor here that has a really large value. And the way that we create a differential amplifier that way is we have to add this really large buffer stage, which will point the input at an infinite input impedance terminal. So in this case, the op-amp, because the input is now directly hitting the op-amp's input terminal, it's got an infinite input impedance. So it doesn't care, if it has, if the input cannot drive a large current, because there's no current that's needed to drive the op-amp in this case. And this instrumentation amplifier has what it does in this stage. So the second stage is the same as the differential amplifier, but the voltage here that gets buffered through this like really weird looking contraption. What this is it makes the difference between these two voltages amplified by some ratio determined by these three resistors. So to understand how this stage works, first let's think about what we could do to not have this stage. So if we wanted to normally buffer, these two input voltages, what we could do is we could simply just add two of these unity gain buffers, right? We could add two of these, one supplying each input voltage, and then we could now basically guarantee that the instruments that are supplying the voltage, their output impedances no longer impact the circuit. But we can also do a config like this, which also amplifies the difference of the voltages. So not just having a unity gain, but we could also amplify it. And the reason why this amplifies the difference is that you can imagine the current flowing through this node, right? The current flowing through this node is just the output voltages, the difference between the output voltages divided by these three resistors. So 5K plus 10K plus 5K. And the difference between this resistor is the difference between the two input voltages divided by this resistor. So that's the current through this resistor. And the current through this segment is the same as the current through this resistor because of Kirchhoff's current law. So therefore, when you expand the math, what you get is the difference between these two voltages multiplied by a resistor constant, which is 1 plus 2 times this resistance divided by this resistance. And yeah, so I just went through the derivation with you, but obviously I don't have the ability to show the mathematics on paper. But you can follow my derivation and come to this conclusion that the gain on this circuit, not only does it have, infinite input impedance now, it also has a gain of 1 plus 5 divided by 1 plus 2 times 5 divided by 10, which in this case is 1 plus 2 times a half, which is 2. So now we have and notice that this is the difference of the voltages that are being amplified. So we don't actually know what the voltage here and here is, right? It entirely depends on the inputs. But we know that the difference between the two is now multiplied by 2. And this circuit will measure that difference. So what we expect is the output is going to be this minus this times 2. So let's have a look at that and see if it's true. So here we have 5 volts minus the sine wave times 2 should be the output. So let's have a look at that. And that's true. So you have this 5-volt input minus 2 times, actually that's not true. Hang on, give me a second, let me figure out the calculations. Yes, my calculations are actually slightly wrong because it's flipped the other way around. The gain is basically the negative of that. So in this case, my V1 is 5 volts, and so it's basically V2 minus V1 times 2. And you can see here that 0 minus 5 is sorry, my bad. It's 5 minus 0 times 2, that's right, so that's 10. And then here you've got 5 minus 1, that's 4, times 2, that's 8, so it is correct, yes. And then you've got here, like at this point, you'll notice that it's supposed to be 5 minus 1, which is 6, times 2, which is 12. But you can see it clips off at the output. That's because the supply rail to this op-amp, right, this op-amp here, only goes to 10 volts. Sorry, this op-amp here. So because it only goes to 10 volts, it cannot supply 12 volts to the output. So therefore, it clips it. But if we supplied, let's say 20 volts here, then we'll get the perfect sine wave back out again. Cool. So, yep, that's it for this video. In the next video, I'm going to go over probably logs and anti-logs.